All right, so now we are going to do section 3.4, or sorry, 6.4, which is just going to be using all of these common Maclaurin series and Taylor series that we worked our way up to in various different forms: limits, derivatives, integrals, algebraic manipulations, and so on. So we're going to start off with a list of just some common ones. So the geometric, we used a ton so far. The geometric power series is a classic one. The main thing to remember, though, about the geometric is it does have a smaller interval of convergence. So its interval of convergence is only for x between 1 and -1. We also figured out how to manipulate a lot of other functions to look like this as well. So keep that in mind. E to the x, we were able to find the Taylor series for that. This is a Maclaurin series, so centered at 0. Is the sum from k equals 0 to infinity of x to the k over k factorial. I didn't prove the interval of convergence for this one, but you could do the ratio test really quick if you'd like, and that one did converge for all real numbers. Last video, we did prove the interval of convergence for the sine of x Maclaurin series, which also converged for x between -infinity and infinity. Similar to cosine, but cosine was with even numbers or even exponents instead of odd. And then tangent inverse we talked about as well, and it has an interval of convergence between 1 and -1. That one happens to be including the 1 and -1, whereas geometric is not. Okay, so here is a list of some common Maclaurin series that we need to know. Now I'm going to keep scrolling back to that list, and we're going to use it a lot in section 6.4, which is how do I work with Taylor series? And I would maybe make yourself a little note that we are doing Taylor series and Maclaurin series. They're all kind of go hand in hand. The only difference is a Maclaurin series is centered at 0, and a Taylor series might be centered at 0, but it might not be. All right, so here is an example. Evaluate the following limits using the Taylor series or Maclaurin series of the functions involved. So here I'm taking the limit as x goes to 0, so I should use Maclaurin series centered at 0. If this were the limit as x goes to 1, you should do a Taylor series centered at 1. Every single time, just think about how the limit is going to be set up. So here I could do L'Hopital's rule, I could, but the specific question is asking to use Taylor series. So let's make sure we know what the question is saying. When I say use Taylor series, what I really mean is to turn everything in the problem into a infinite or not infinite, depending on what's given, polynomial. All right, so do we know the power series for e to the x? We do. I'm going to write it down just so I don't forget. So e to the x is 1 plus x squared over 2 factorial plus x cubed over 3 factorial, etc., etc., etc. I just wrote it down as a polynomial. We also have it as series notation, which is the sum from n equals 0 to infinity of x to the n over n factorial, and that converges for all x. I just copied that down from the previous page. That's really what I did. Okay, so I'm going to plug that in. So this limit becomes the limit as x approaches 0 of, I'm going to plug in exactly what that polynomial is for e to the x. So I still have a fraction, and e to the x becomes 1 plus x squared over 2 factorial plus x cubed over 3 factorial. Don't forget the dot, dot, dot. It has to have the dot, dot, dot. Otherwise, it would not be correct. This is, in fact, an infinite polynomial. And then minus, and then I'm going to do the same exact thing for e to the -x. But e to the -x just means all of these x's get replaced with a -x, right? This is the composition of functions that we did in 6.2. So 1 plus -x plus, and then if I plug in -x squared, the negative goes away. So then I end up with positive x squared over 2 factorial. But then if I plug in -x here, -x cubed stays negative. So -x cubed over 3 factorial, etc., 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 all over x. I turned everything, and I mean everything, into a polynomial. E to the x and e to the -x were infinite. The denominator happened to already be a polynomial. It's finite, but it's already a polynomial, so I can leave it as it is. You turn everything into a polynomial, finite or not. Okay, and then I just plug and chug. Okay, so then I'm going to simplify, plug and chug. This will become the limit as x goes to 0. You will see that if I were to distribute this negative across, which is exactly what I'm going to do, you might have to pause and do some algebra there. Distribute that negative right across that parentheses and combine some like terms. When I distribute that negative and combine some like terms, we're trying to see what happens here. It ended up with the 1 gone, and then I end up with an x plus x, which is 2x, plus the X squareds were gone, but there were 2 of the x cubed over 3 factorial. And you can imagine that the x to the 4th would have been gone, but there would be 2 of the x to the 5th over 5 factorial, etc., all divided by x. Then I break up the fraction. And each one of those terms is going to be divided by x. So that turns into a 2 plus a 2x squared, over 3 factorial plus a 2x to the 4th over 5 factorial, etc. I no longer have a fraction. If I plug in x equals 0, everything is gone except for that first one. So my answer was 2. Ta-da! All right, let's do the same thing. So I'm going to scroll back up to our list of common Maclaurin series, and I'm going to capture the one that is going to be needed for the next problem, which was cosine. So I'm just going to capture the cosine one and have it maybe right next to me so I can visualize the need here. We're taking the limit as x goes to 0, so I want the Maclaurin series, and this problem has a cosine in it, so I grabbed the cosine one. The difference is this one has a cosine of 2x. So I need to replace all of those x's in that infinite polynomial with a 2x. Let's do that. The limit as x goes to 0 of, I'm going to run out of space. Let me see if I can simplify this a little bit better. 2 times cosine becomes 1 minus 2x squared over 2 factorial plus 2x to the 4th over 4 factorial. I always like to have a few more terms. I need to recognize a pattern. So don't do the dot, dot, dot too early. Maybe do one more. So plus, I can recognize the pattern. I think the next one would actually be minus because this is alternating. So minus 2x to the 6th over 6 factorial. I like to do at least one more. I still have a minus 2, a plus 4x squared, and an over 2x to the 4th from the original. Okay, then I do the algebra. So pause to do the algebra. Distribute the 2. The what cancels. When I distribute this 2, I'm going to end up with 2 minus 2 is gone. 2x squared becomes 4x squared, but over 2, it becomes 2x squared times 2 is 4x squared, but with a negative and a positive, that one's gone. And let's keep going. So I ended up with the limit as x goes to 0. We just have to simplify along the way, and it's not always easy. I ended up with 2 to the 4th, which is 16 times 2, which is 32, x to the 4th over 4 factorial minus 2 to the 6th times another 2 is 128 over 6 factorial times x to the 6th, etc., but all over a 2x to the 4th. When I break up the fraction, that gives me the limit as x goes to 0 of 32 divided by 4 factorial divided by another 2. Yeah, okay, then minus 128 x squared now over 6 factorial with another 2 divided by it. But now I plug in x equals 0, and all the other ones are gone except for that first one, which is 32 divided by 2 times 4 factorial, which feel free to use your calculator, and I got 2/3. All right, so same thing for the next one. Let me go back up and grab the power series that I need. In this case would be the arctangent. So that way I have it in front of me, just right here off to the side. And I return everything into a polynomial, right? Turn everything into a polynomial. So this will become the limit as x goes to 0 of 3 times tangent inverse is x minus x cubed over 3 plus x to the 5th over 5 minus x to the 7th over 7. Don't forget your dot, dot, dot. Minus 3x plus x cubed over x to the 5th. Pause, distribute, combine your like terms. The 3x would have canceled. The x cubed would have canceled. And I got 3x to the 5th over 5 factorial minus 3x to the 7th over 7 factorial dot, dot, dot divided by x to the 5th. But now I'll break up the fraction, and each one of those are divided by an x to the 5th. which made that just a 3 over 5 factorial. I don't know where the factorial came from. That they're not factorials in tangent inverse. Those were not there. So sorry, I don't know why I threw those in there. I meant to copy it. There we go. I ended up with everything going to 0 except for that first one, which was 3/5. Ta-da. Cool. All right, so that's limits. Now let's do derivatives and then integrals. Yeah, just one of each time, okay? So same thing now for the next one. This one is kind of an interesting one. It's just a verification. I'm asking you to find the derivative of e to the x. That's what I'm asking. You already know what the answer had better be. The derivative of e to the x better be e to the x. We can't have used all this work and messed up math. So we know what the answer is supposed to be. We are just verifying that these Taylor series still work. So when I say about, I still mean centered. So use the Taylor series centered at 0. That means the Maclaurin series. And so let's write out what the Maclaurin series for e to the x is. So in this case, my function is e to the x, which we know the Maclaurin series from that couple pages ago, and I'm going to go ahead and just write it down now. It's 1 plus x squared over 2 factorial plus x cubed over 3 factorial plus x to the 4th over 4 factorial plus x to the 5 over 5 factorial, etc., etc., etc. And I'm going to give myself some space there. It does have the power series representation of the sum from n equals 0 to infinity of x to the n over n factorial. Quick reminder, the interval of convergence for e to the x was negative infinity to infinity. This question didn't ask that, just thought I'd remind you in case it does. Now I'm going to take the derivative, but remember, whatever you do to one side of the equal sign, you have to do to the other. So I'm going to write that in a different color so you realize that I wrote down the equal sign first, and then I'm going to take the derivative of both sides, which in this case is all 4 sides of that equal sign. On the left, f prime is equal to, I know this had better be e to the x, because I remember Calc 1. The derivative of e to the x is e to the x. Let me, for just now, leave it blank. I know it's going to be e to the x. Let me leave it blank for just right now. The derivative of 1, let's make it easy. The derivative of 1 is 0, plus the derivative of x is 1, plus the derivative of x squared is 2x, but I still have that over 2 factorial, plus the derivative of x cubed is 3x squared, but I still have that 3 factorial, plus 4x cubed over 4 factorial plus 5x to the 4th over 4 factorial, etc., etc., etc. All the way on the right side, sorry about that, all the way on the right side of that equal sign, this is going to become the sum from n equals 0 to infinity of nx to the n minus 1 over n factorial. I'm going to zoom in on the right-hand side for a second because that's going to be really important. All I did is I just brought that power down. Excuse me. Sorry about that. I brought the power down and subtracted 1 from the power. But look at the starting value. If I start by plugging in n equals 0, doesn't that just give me 0? I don't need to start at 0. Remember that. We got to be very careful with that. I don't need to write that first term. I actually want that to start at 1. Okay, let's zoom back out. We got this. So I took some derivatives. Let's simplify. Let's simplify what we can. So over here, I have a 0 plus 1. I did not need to write that 0. And you do not need to write that 0 plus. Plus, now 2x over 2 factorial is just x. Plus 3 over 3 factorial. Remember what factorial is. 3 factorial is 3 times 2. With a 3 on top, the 3 canceled, and I got x squared over 2 factorial. Same thing. 4 factorial is 4 times 3 times 2. The 4 cancels, and it becomes an x cubed over 3 factorial. 4 this was supposed to be a 5 factorial. Okay, 5 factorial, I'm so sorry, is 5 times 4 times 3 times 2. With the 5 on top, that becomes an x to the 4th over 4 factorial. Doesn't that look familiar? 1 plus x squared over 2 factorial plus x cubed over 3 factorial, etc., etc. Didn't I get right back to where I started from? Yeah, which means the derivative of e to the x is e to the x. We already knew that, but it's really cool to see that the Taylor series still give us that same exact result. On the other side of that equal sign, if you remember, if you want to change the index, if I want the index to go down by 1, if I want this index to go down by 1, everything else has to go up by 1. So that becomes an n plus 1 times x to the n over n plus 1 factorial. But remember how factorials work, n plus 1 factorial. As a quick reminder, n plus 1 factorial is n plus 1 times n factorial. So the n plus 1 actually cancels, and I really do get x to the n over n factorial. So I have just proved that the derivative of e to the x is still e to the x. Ta-da! Okay, let's do the same thing with a few other ones. We're going to do the same idea, but with integration. So we've done limits, we've done derivatives. Let's do an integral. Let's just keep on working with these Taylor series. So this next one is to approximate the value of this definite integral using a numerical method. I am not going to do the trapezoid rule. I'm not going to do the Simpsons rule. Taylor series is another numerical method to find the value of a definite integral. Let's write down some things that we know. I know the Taylor series, or the Maclaurin series, because I'm going to center this at 0, for e to the power of x is 1 plus x squared over 2 factorial plus x cubed over 3 factorial plus x to the 4th over 4 factorial, and so on, which has the sigma notation as the sum from n equals 0 to infinity of x to the n over n factorial. Cool. So I want to use that to do this integral. My integral is the integral from 0 to 0.25 of e to the negative x squared dx. I'm going to look at the thing that I know, which is e to the x, and replace it with the composition that I have, which is e to the negative x squared. So every x is going to turn into a negative x squared. So I'm going to leave the integral, the bounds from 0 to 1/4 on the outside. Let me come back to the integral later. Let me start with the inside, which is the integrand. And it's going to become the sum from n equals 0 to infinity of negative x squared to the n over n factorial. Okay, pause what you're writing and just watch with me. I just took this x and replaced it with the negative x squared that I had in my e to the something. Okay, I don't know if we saw that. Let me highlight that one more time, right? In my original Maclaurin series for e to the x, I replaced my x with the negative x squared because I don't have an e to the x, I have an e to the negative x squared. Okay, let me simplify that from here because there's definitely still a lot. I'm not going to do the integral quite yet. The integral from 0 to 1/4, I'm going to leave it alone. I'll come back to that later. We got bigger things to worry about right now. Let's worry on the inside first. The sum from n equals 0 to infinity. This is now alternating negative 1 to the n because I have a negative 1 to the n. X to the 2 to the n becomes x to the 2n over n factorial dx. I just simplified. Okay, now I'm going to just do an antiderivative. We actually know how to do an antiderivative. I know I can add 1 to the power, divide by the new power. I already know that, so now I think I'm going to. So this will become the sum from n equals 0 to infinity of negative 1 to the n, x to the 2n plus 1 over n factorial stayed there because it was a constant multiple, but I need to divide by the new power. I just did an antiderivative. And I'm going to highlight what I did the antiderivative of. This is the only thing I needed to do the antiderivative of. Everything else was just a constant multiple, and so it stayed. And then I'm going to plug in my bounds because I did have a definite integral. So I've got from 0 to 1/4. Let's plug in some numbers. These numbers are going to get a little bit uglier, so now I'm going to plug in some numbers. This will become the sum from n equals 0 to infinity of negative 1 to the n times 1/4 to the 2n plus 1 over n factorial times 2n plus 1 minus the sum from n equals 0 to infinity of -1 to the n times 0 to the 2n plus 1 over n factorial times 2n plus 1. I wrote that kind of sloppy on purpose because 0 times all those numbers are just going to go to 0 anyways. So that guy is actually gone. All right, so then this is the thing I now need to evaluate. Let me start plugging in some numbers now. Now I'm going to just plug. I already did the antiderivative, so that's pretty good. I also plugged in my bounds, so that's pretty good. When I plug in numbers now is from my index. I'm going to start off by plugging in 0. 0 factorial is 1. -1 to the power of 0 is 1. 1/4 to the power of 2 times 0 plus 1. So if I plugged in 0, this ended up with 1/4 to the power of 1 over 1 minus. If I plug in 1, this becomes negative. That's where the minus is coming from. If I plug in 1, this becomes, 1/4 to the power of 3 over 3. No, I'm just going to plug in a next number. I plugged in 0, I plugged in 1. Now I'm going to plug in 2. I got 1/4 to the power of 5 over 2 factorial times 5. I'm going to plug in, I plugged in 0, 1, 2. I'm going to plug in 3. I'm just plugging in until I run out of space. 1/4 to the power of 7 over 3 factorial times 7. And I suppose I could keep going. Plug in a whole bunch. Maybe you want to plug in 25. I don't know. We got calculators, so just keep going. Add them together, you're going to get a number. But I'm gonna let me do that with my calculator. Actually, let me start plugging that in. So I'm gonna use decimals. You can use fractions if you prefer. I'm just gonna choose to use decimals because these decimals are gonna get a little bit crazy. I ended up with 0.25 minus 0.005208 plus, and then this one was a little bit tricky to plug into my calculator. So be patient with yourself. When I typed it in and I got 9.765 times 10 to the -5. That's what I got. And then minus, and then the same thing for this one. When I typed this one into my calculator, I got 1.45 times 10 to the -6. And then I just ran out of space, so I stopped typing that into my calculator, but that's what I got. And I suppose now I could add those up for sure, but when do I stop? Let's pause and go back to the original question. The question says to approximate the value of this definite integral using Taylor series. So far, we've done that. With an error less than 10 to the -4. That's what we need to do. With an error less than 10 to the -4. Look at all the work I did so far. At the very end of what I've got so far. Is that an alternating series? Yeah, it's not a power series anymore. I got numbers. This is just adding up infinitely many numbers. This is just adding up infinitely many numbers. And it is alternating infinitely many numbers. So this is an alternating series, not an alternating power series. This is an alternating series. And I'll scroll up one more time. I want that error to be less than 10 to the -4. Remember, the absolute value of the remainder was less than or equal to the first neglected term. That was from section 5.5, alternating series, earlier on in this unit. Alternating series. So I want my remainder to be less than or equal to, well, I know it's less than or equal to a sub n plus 1, but I want it to be less than 10 to the -4. So which one of these is less than 10 to the -4? Yeah, that's really all it is. Rather than me have to do a whole kinds of algebra, I already have the numbers, right? Which one is less than 10 to the -4? That one. Well, that one plus all the other ones, yeah. So that one is less than 10 to the -4, which means that this one should be my first neglected term, which means we only need to add up the first two terms. So 0.25 plus 0.005208. Sorry, that got kind of sloppy. And I got 0.255208 is my estimated value of that definite integral. Ta-da! Awesome. We have a couple more. We still have a couple more, so bear with me. I got 2 more to do. The next one is use Maclaurin's series for tangent inverse to evaluate this guy. All right, let's go back and find my Taylor series for tangent inverse. So I'm going to go back and find it. I'm going to grab the one I need for a tangent inverse just so I have it in front of me, have it right next to this. This is what I know. I know that tangent inverse of x is equal to this infinite polynomial, which looks kind of close to my question. Tangent inverse of x is the sum of -1 to the k, x to the 2k plus 1 over 2k plus 1. My question looks identical, but without an x. So what should I make my x be to make that series match this? If x were 0, it wouldn't be matching, because if x were 0, it'd be 0. Everything would be 0. But if x was 1, then that series in my tangent inverse series would match my question. So let's write that down. So tangent inverse of 1 would become the sum from k equals 0 to infinity of -1 to the k times 1 to the 2k plus 1 over 2k plus 1. I just replaced my x with 1, and then now that I've done that, I also notice that 1 to the power of 2k plus 1 is just simply 1, so I end up with -1 to the k over 2k plus 1. Isn't that my question? Cool. So what's tangent inverse of 1? It's pi fourths from your unit circle. So that means if I were to add up all of those numbers, 1 minus 1/3 plus 1/5 minus 1/7, and if I were to do that forever, literally forever, if I were to do that forever, then it would equal pi fourths. So if you ever wanted to know what pi was, just multiply both sides by 4. Pi is 4 minus 4/3 plus 4/5 minus 4/7 forever. This is the coolest part of Calc 2. So pause where you're at, pause the video and go get a calculator. Now you're back in your calculator. Don't type in pi. Type in 4 minus 4/3 plus 4/5 minus 4/7. Maybe do one more, plus 4/9 minus 4/11. You've got a pattern going on. You know that every other one should be negative. I forgot a negative. I made all of mine positive. That will be wrong. There we go. And you'll see that you're going to get closer and closer to about 3.14. I went up to 17 and I got 3.1. So I'm just saying, that's how you can figure out what pi is. Pretty cool, I thought. All right, let's do the one more. Let's do one more because we made it this far. So f of x is equal to e to the x minus 1 over x. For x not equal to 0, just don't divide by 0. Okay. All right, use Taylor series, centered about 0, so that's the Maclaurin series, to evaluate f prime of 1. Let's find a derivative. We can find a derivative. So let's do this. F of x is equal to e to the x minus 1 over x. What do I know about e to the x? I already know the Taylor series or the Maclaurin series for e to the x. You can go back and look at that list of those 5 common Maclaurin series. E to the x was one of them. Let me write it down. E to the x is 1 plus x squared over 2 factorial plus x cubed over 3 factorial forever. So that's 1 plus x squared over 2 factorial plus x cubed over 3 factorial forever minus 1 over x. The ones canceled. The ones canceled. Break up the fraction. And I ended up with 1 plus x over 2 factorial plus x squared over 3 factorial. You can imagine the next one would be x cubed over 4 factorial and so on. And I have a sigma notation for that as well. You can start to recognize a sigma notation for that if you'd like. Let's do that. That means this is going to become the sum from n equals 0 to infinity of, it looks like it's x to the n over, to me it looks like the denominator is always 1 higher than the numerator, still having a factorial. Cool. So now that is my e to the x minus 1 over x. Cool. It did say to find f prime of 1. So now we just find f prime. I'm going to take the derivative, but remember, whatever you do to one side of the equal sign, you must do to the other side of the equal sign as well. So I'm going to do the derivative on both sides. F prime of x, quotient rule. Low d high minus high d low all over low squared. From here to here, quotient rule. Quotient rule from Calc 1 equals the sum from from n equals 0 to infinity. Bring the power down, subtract 1 from the power. Bring the power down, subtract 1 from the power. It said, what did it say? I think the question said for me to find, I have to scroll back up. It said evaluate f prime of 1. So that means I should plug in the x value of 1. We can do it. F prime of 1. 1 times e to the 1 minus e to the 1 minus 1 all over 1 squared, which simplified by the way to 1. I'm going to rewrite that. That's simplified by the way to 1. All that work, the e's ended up canceling. I plugged in 1 after that quotient rule and I got 1. 1 times e to the 1 minus e to the 1 minus 1 all over 1. Simplified to 1. Equals, plug in x equals 1. The sum from n equals 0 to infinity of n times 1 to the n minus 1 over n plus 1 factorial, and 1 to the power of n minus 1 is, of course, just 1. So did I find the value of this infinite series? I did. It's 1. So the answer to all that, if I added up those infinite numbers, if I plugged in 0, I got 0. If I plugged in 1, I ended up with 1 over 2 factorial. If I plugged in 2, I ended up with 2 over 3 factorial, and then 3 over 4 factorial. And if I did that forever, it converges to the number 1. Ta-da! All right, this is just one more time that list of common Maclaurin series. Remember that Maclaurin series means centered at 0. So all of those ones had the center at 0. Remember the interval of convergence was important because it didn't always converge for everything, but sometimes it did. That's it for power series. See you next time.